Hello, everyone. Welcome to your first lecture of the semester. So these are your lecture notes that are posted and found on Canvas. So please go ahead and download these. So we'll start by talking about chapter 2, the basic concepts of set theory. So this chapter is all about set theory. We'll begin section 2.1, which are just talking about very simple symbols and terminology. So section 2.1 are just involving symbols and terminologies. So just get you started on the notation that we'll be using this semester and through this chapter, more especially called set theory. The objective of this section is to make sure that you understand the three methods to designate sets. We're going to talk about what are sets. We're going to be recognizing important categories of numbers and determine the cardinal numbers of sets and what does it mean to be a cardinal number. We're going to be distinguishing between what is a finite set and an infinite set. We are going to determine if two sets are equal or not equal. So these are the objectives of this section. Okay. Let's start by talking about designating sets. So before we talk about how to designate sets, well, we need to know the definition of a set. So a set is a collection of objects. The objects belonging to a set are called elements or members of the set. And these are the three ways to designate a set. It can be a word description or a sentence, listing method, and the set builder notation. It could be described as a sentence, as a listing method, and a set builder. So a set builder, it's such as X such that X is blank. This is set builder. A listing method, well, you're just listing them out, and word description is just a sentence. Writing it out. Okay. So we're going to look at some examples. Let's look at designating sets. So we have an example here. The set of even counting numbers less than 10. So the set of even numbers, counting numbers less than 10. What are the even numbers that are less than 10? Let's list them out. So that'd be 2, 4, 6, and 8. Here is the listing method. This reflects this sentence, the set of even counting numbers less than 10. Now in set builder, it's again X such that X is a positive, or X is an even number, even counting less than 10. So pretty much you're rewriting the statement. X is an even counting number less than 10. So the word description and the set builder, they have some common things because you're pretty much rewording it, except it has this little curvature on the parentheses. But the listing method, you are listing them out. So this is an example of how it looks like to designate sets in the three different methods. One method, two methods, third method. Okay. Again, designating sets. Now here, see how this is a listing method? This example A is written in a listing method. Sets are commonly given capital letters. So A, the set A is equal to 1, 2, 3, or 4. So this is the set A. The set containing no elements, it's called the empty set. So there is an empty set called the null set. So an empty set, it can look like two ways. You have brackets by themselves or this symbol called the empty set. They both represent the same thing. To show that 2 is an element of A, we're going to use this element symbol. This symbol, this E, is another notation. It means that your element, so see how 2 is part of the set? So 2 is part of it. 1, 3, and 4, they're all part of the set. So 2 lives. This E, it means it lives in the set. Okay, it lives in the set. A does not live in the set. So A is not part of the set. So it doesn't live in the set. Notice how A is not. So here this means it's an element of. And then when you have an element and a cross, this is not an element of. Okay, so make sure you're writing that down. I'll give you a few minutes. So what it means to be an element of an empty set. Example 1. We wish to give a complete listing of all of the elements of X such that X is a natural number between 3 and 8. Now this, what type of designate does it have? It has designated as a set in set notation, set builder notation. So if it's between 3 and 8, a natural number means like a whole number, except it doesn't contain zeros. So the numbers are 4, 5, 6, and 7. 4, 5, 6, and 7, because the word between, it actually excludes the endpoint. So not including 3, not including 8. So all of the numbers in between 3 and 8. So 4, 5, 6, 7. So again, it's like if you have a value and you are excluding 3 and 8. So what are the numbers in between? Okay. 3 less than X less than 8. So that would be 4, 5, 6, and 7. And of course, these would be such that X is a natural number. Okay, so you are excluding. The word in between excludes the endpoint values. Now we are applying the set symbol. Let's look at example number 2. Determine whether each statement is true or false. This means that 4 is an element of 1, 2, 5, 8, and 13. Is that true? Is 4 in here? No. So this is false. Because 4 does not live in 1, 2, 5, 8, or 13. It's not in there. It's false. 4 is not an element of the set. Therefore, it's false. What about B? 0 is an element of 0, 1, 2, or 3. Yes, that's true. Because 0 lives in the set 0, 1, 2, and 3. That's true. Now the next one. Does 1/6 does not live in 1/3, 1/4, and 1/5? Yes, that's true. Because it's saying it's not an element of. So 1/6 is not an element of the set. So that's true. So these are some examples of applying set symbols. So far, so good. Again, this is just to get you started on the notation of a set. What does it mean to be a set? What does it mean to be an element of? Set of numbers. So numbers have different types of numbers. We have the following. We have natural numbers. These are the so-called counting numbers that does not involve zero. So just 1, 2, when you're learning how to count when you're a child, 1, 2, 3, 4, just counting numbers. A whole number is you do have 0. You start with 0, 1, 2, 3, 4, 5, so on. We have integers where you have positive and negatives. And why do we need this? Because we're going to be using set to distinguish integers, whole numbers, natural numbers. Rational numbers are fractions where their denominator, of course, is not equal to 0. We don't have any repetition. So natural numbers. Irrationals, you cannot write it as a fraction, like the square root of 2, the square root of 3. Those are irrational. And real numbers, it's exactly anything. It can be a decimal, a fraction, a whole number, anything. So we have 1, 2, 3, 4, 5, 6. 6 different sets of numbers. But the real actually incorporates all of them. It's the big pack, the real numbers. Okay. So hopefully you're writing this down. Again, you do have these notes in front of you. Now let's talk about another definition. And that definition is called cardinality. So what does it mean to be a cardinality? The cardinality is the number of elements in a set. It's called the cardinal number or the cardinality of a set. So the number of elements tells you the cardinality. So the number of elements tells you the cardinality. So it has a symbol N of A, which represents the cardinal set of A. Excuse me. So N of A, it means I want you to tell me how many elements live in that set. It's a cardinal number or a cardinality. Let's look at finding cardinal numbers. Find the cardinal number of each set. So I want to find N of K. Oops. N of K, the cardinal of the set. Okay. And 1, 2, 3, 4, 5, 6. 6 is a cardinality of K because I have 6 elements inside K. What about M? The cardinality of M is only 1 because you only have 1 element inside the set M. And then will the empty set, well, the cardinality of the empty set is 0. You don't have any. There's the empty set. It's empty. You don't have any. So the cardinality of K is 6. The cardinality of M is 1 because you only have 1 element and that element is 2. And the cardinality of an empty set, because it's empty, you do not have anything inside that set. Let's talk about what makes a finite and an infinite set. Well, if the cardinal number of a set is particularly a whole number, we say that there is a finite set. However, when the set is so large, its cardinal number, it's not found among the whole numbers, we can call that an infinite set. So for example, all counting numbers, that's infinite because counting numbers go on forever. All even numbers, that's also infinite. Numbers in between 5 and 8, that's finite. So we're going to be looking at some examples of infinite and finite sets. So we want to designate all odd counting numbers by the 3 counting methods. So we wish to do all 3. So the first one is the word description. The set of all odd counting numbers. The listing method is 1, 3, 5, 7. Again, they're the counting numbers by 3 counting methods of set notation. The set of all numbers, 1, 3, 5, and then set builder is X such that X is an odd counting number. So all we want is this piece, odd counting number, odd counting number, odd counting number, and odd counting number. So pretty much using an example, we were able to write our solution in 3 different ways. We were able to have a word description, we were able to list and do a set builder. The last part of this section is talking about equality of sets. What makes two sets equal? Set A is equal to set B if all the elements of A are in B and all of the elements in B are in the elements of A. So they must have the same elements. Every element of A is in B, every element of B is in A. Determine whether two sets are equal. Well, let's say that A is -5, 2, 6, and 7, and let set B be -5, 0, 2, 6, 7. Let's see. Well, -5, -5, 2 and 0, 2 and 2, 7 and 7, and then, well, wait a second. I don't have a 0. So element B has a 0. However, 0 is an element of the second, but not the first. So these are not equal. If one of them misses, it doesn't matter. They are not equal. They must have the identical elements. So the first example, the two sets are not equal because they have a difference on the 0. We're determining whether two sets are equal. Decide whether it's true or false. So I have A, B, C, and D, A, C, D, B, same. So I have an A, I have an A, I have an A, I have a B, I have a B, I have a C, a C, a D, and a D. See how all of them matched? It doesn't matter. The order does not matter. They have the same elements. Therefore, they are equal. Now this one, 2, 4, 6, and X such that X is an even number. Well, this is true on this side. A is in B now, but B is not in A. Why? Well, X is an even number, 8, 10, 12, 14. So here, this is first of all, this is an infinite set, and 2, 4, 6 is a finite set. So no, false. 2, 4, 6 does not represent all even numbers. So see how all of the even numbers are not in A, so therefore they are not equal. Okay. And that is the end of section 2.1. Okay. So hopefully everything is making sense. We'll pause and then we'll start in section 2.2. Thank you.